Hello, today we will answer question A from SCUDEM Challenge 2022. We are three students of Karazin Kharkiv National University, Mykola, Oleksii, and Nikita, and our coach Nataliia Goncharuk. Okay, I will introduce you to the problem. Two groups of people, we call them specialists and newbies, are performing on ISS. Of course, they're stressed, but at the same time, they want to do everything they can for successful work. So our task is to predict how various factors affect their stress and productivity. We made some assumptions that can approximate our model, and also we found that productivity depends on stress according to Yerkin's law.
The R is some value between 0 and 24 that represents the hours of rest per day. You can see here that we imply that they rest exactly TR halved hours in the morning and TR halved hours in the evening. However, further on in the model we will move to defining the workday simply as the start point and the end point. We call the set TW as the set of the working hours and TR as the set of the resting hours. The expected serves to express the daily work schedule. We understand it as some function that images the set TW on the segment 0, 1. It represents the productivity that members of the crew are expected to match during the workday. The schedule deviation coefficients express how the deviations from the schedule, either underperformance or overworking, affect the stress level of the team. The stress perception coefficients express how the average stress in the team affects the stress of each group. The work exhaustion coefficient expresses the change of stress due to exhaustion from work. Rest influence coefficient expresses the change of stress while resting. Interest coefficient expresses the stress induced to group 1 by the additional attention required by group 2. For group 2, this coefficient is 0. Effort parameter expresses the efforts to match the schedule. It influences directly the productivity, unlike the parameters we discussed before that influence stress. Stress influence on productivity. It expresses how important the level of stress is to productivity. Note that it's reasonable to put those coefficients at least 5 times greater than the previous ones, so that productivity won't be more dependent on the schedule itself than on the stress change related to this deviation. Before we begin to formulate the model itself, we have to define one additional function in order to simplify the notation. The heaviside step function turns 1 for any non-negative x and 0 otherwise. Thus, if we take such combinations of functions as presented on the screen, we will get the function that turns 1 for all t in the period of working hours and 0 otherwise. Now we can present the equations themselves. The stress equation looks the following way. We will break down every component right now. The schedule deviation perception works the following way. If productivity is greater than the expected one, the team overperforms and its component is negative, which results in stress reduction. If they underperform, it's positive, which results in stress buildup. The more they deviate from the schedule, the more the influence is. The modified heaviside step function represents that this matters only during the work hours. This component works like this. The function p represents the fact that the harder the work is, the more exhausting it is. The modified heaviside step function serves the same purpose as previously. Influence of average stress works so. Firstly, we calculate the average stress. We subtract 1/2 so that if stress is below average, this results in stress reduction, above average in buildup. In this component, 1 minus the modified heaviside function turns 1 for rest hours and 0 otherwise. The function S2 is present in rest influence in order to show that the more nervous the second group is, the more trouble they cause. Those are perception equations. We will also break down every component. The effort influence works like this. They will work harder if they are behind the schedule and will pay less effort if getting over the schedule. The component basically works similar to the component in equation for stress. This component is a derivative of a Gaussian function we saw earlier. The whole system looks like this. We impose the condition that p and s vary from 0 to 1. However, our current system does not satisfy this. Consider the following equation above that has some solutions that take values from r. We want to get some equations represented as shown below so that its solutions take values from 0 to 1. Consider the segment function. It images the real numbers on the segment from 0 to 1 and is monotonely increasing on r. Following the steps described on the screen, we can get the following equation. We want the function g to be dependent on the new function directly, not to keep the relations it had before. Thus we make the following substitution and get the desired equation. We want our model to be capable of modeling through long periods of time, keeping the assumption that the schedule for every day is approximately the same. If we consider the function you can see on the screen, by substituting t with tau t in modified heaviside function and p expected, we will get the desired result. The arbitrary nature of p expected complicates the modeling process. We simplify it by viewing it as a linear interpolation through 4 following points, where t coordinate of the first and the last one matches respectively start and the end of the workday. Note that when we will search for optimal schedule, we will add 4 more points between the first and the last one. Those are the parameters we chose to use while modeling our system. We chose them considering the skill difference between the novice and the trained group and the fact that we want productivity to depend on stress much more than on schedule. We chose the following initial values for stress and derived productivity from our Karazin function.
Let's visualize our model and make a few points. Okay, there is just simple representation of our model. We expect a scope of work is area under green line. You can see that they don't work when the green line go to zero. Also, further, you will most often see graphs on which groups are separated. This is done to more clearly show some things, but underneath they work together. For example, in this slide, we can see that newcomers are encouraged upon arrival. However, their stress increases faster while specialists are more stable. Here you can see the display of the previous two plots for the entire crew. To show that our model behaves quite realistically, let's first consider a schedule in which the crew is highly loaded, and then consider when the crew almost does not get tasks. As you can see, when the crew is loaded, the stress of the crew becomes maximum and the productivity is minimum. Also, we can see that specialists can withstand a little longer under such a load. When the crew receives a few tasks, they quickly relax and stop working, but at the same time, they do not give in to stress. Two plots are shown here. One of them shows the work during the day, and the second shows the same work but with a slight deviation. As we can see, with a small deviation, a small change is obtained. However, how much it affects depends on the coefficient Kw, which shows the dependence of the delay from the schedule.
Now let's test the difference between the gradual and immediate increase of productivity through time. Consider 5 trapezoids of the same area, that means the amount of the completed work is the same in all cases, where each trapezoid has a different angle on the left side. The side can be represented as a segment of a line starting at the point 50 and ending at the point tier 1h. The numbers on the top of slides represent the tier 1 coefficient. The graphs show the faster increase to the lesser value reduces the stress buildup, and in fact, as we can see from these integrals, proves to be more efficient in terms of the completed work, with the greatest amount of work done in case of immediately high level of productivity without any increase. Optimal schedule. When scheduling for stressful work conditions, it is necessary to consider possible issues associated with rapid crew fatigue, as well as a significant decrease in work productivity. To build an optimal work plan, we have to consider the following parameters: the amount of work completed, and respectively the speed of its completion. And we need to maintain an optimal stress level of the crew for productive work and to support long-term productivity. To find the optimal schedule, we use reinforcement machine learning algorithms. We have developed an environment using the OpenAI Gym Python library, in which the agent interacts with the schedule by fitting the coefficients of the p-expected function. With the stable baselines 3 Python library, learning is performed by algorithms based on the reward and punishment system, where the evaluation criteria are the parameters described above. The examples of the algorithm's work show how much the correctly chosen schedule can affect the team's productivity, as well as their psychological state and ability to keep the work pace at a high level. We can see that it is not appropriate to require a constant high workload on the teams in the schedule. The team requires changes in the workload during the workday in order to maintain stability and an acceptable pace of work.
Let's summarize our work. So, we have built a model that shows how the productivity and stress of the ISS crew changes. We made conclusions based on our model that a gradual entry into work is not effective and minor deviations from the schedule are not significant. We have also built an optimal schedule that will help the mission participants to maintain productivity and save nerves. Nothing is perfect, so our model is limited by our assumptions and the inability to take into account some factors. And the disadvantage is that we must conduct a complex, comprehensive study and interview crew members to calculate key factors and initial conditions. To improve our model, we can carry out some transformation and generalize. In that way, some factors will become dynamic and the model itself worked in any proposed environment. Thank you for watching. I hope you enjoyed digging deeper and understanding our answer.